Welcome back. In this video, we're going to take a look at a brief introduction to the idea of energy. So energy, from kind of the physics definition, is the capacity to do work. Okay, we'll talk a little bit later in the year about what that means. But there's two main categories of energy. There's kinetic energy, which is energy of motion, and there's potential energy, which is stored energy. In physics, we talk about this stored energy as height. So if you think of a book, right, the higher I raise a book up, the more potential it has to fall and do work and make a loud noise. So potential energy is represented as height in physics, is related to height in physics. Kinetic energy is energy of motion, right? So when I drop that book, the book moves and the energy is translated from potential energy to kinetic energy. In chemistry, this is going to be a little different. Potential energy is going to be the energy stored in chemical bonds, and kinetic energy is going to be energy associated with the random movement of particles. And we'll talk a little bit more about that in the next video. Energy can't be directly observed. We can only observe it when it changes from one form to another. And a few types of energy we may encounter are highlighted down here, and we'll be talking about those throughout the year. So in chemistry, like I've said previously, potential energy is still stored energy, kinetic energy is still energy of motion, but potential energy is energy stored in chemical bonds, and it's called chemical energy. Kinetic energy is energy of particles moving, which is called thermal energy. And the next video focuses specifically on this thermal energy. When we talk about heat in chemistry, we're talking about the movement of energy from one area to another, specifically from high thermal energy to low thermal energy. And again, that'll be covered in the next video and in a whole unit a little bit later in the year. When we talk about kinetic energy, we're going to relate it to the idea of temperature. So you might think of temperature as how hot or cold something is, but I want you to start thinking about temperature as a measure of the average kinetic energy of a substance. In other words, it's related to how fast the particles are moving in that particular substance. All particles have some amount of movement, right? Now, this is hard to imagine. We can't see gases, but you might be able to imagine that they're moving. They're very far apart. Solids, though, we can see a solid, and it's hard to imagine that those particles are moving, but they are as well. They're vibrating back and forth ever so slightly. If the matter were to stop moving, then it would reach absolute zero, which is the minimum temperature we can have. Okay? And we say the matter would cease to exist if we were able to take a sample and get it to absolute zero. In order to work with temperature a little bit more, we also want to talk about the temperature scales. So we're going to forget about the Fahrenheit scale for now. We measure our temperature in the United States in Fahrenheit with 32 degrees Fahrenheit being water freezing, 212 Fahrenheit being it boiling. But we're going to use the Celsius and Kelvin scales almost exclusively in chemistry. The Celsius scale is convenient because water freezes at 0 degrees Celsius. 100 degrees Celsius is where it boils. The Kelvin scale, however, we like that. That's called the absolute temperature scale because there is a minimum. There's no negative temperatures. So 0 is the minimum temperature on the Kelvin scale, which means 273 degrees higher than that is water freezing, and 373 degrees higher than that, or 100 degrees higher than where water freezes, is the boiling point. What you might notice here is that a change of 1 degree, in other words, going from 0 to 1 degree Celsius, or going from 0 to 100 degrees Celsius, is 100 degrees on the Celsius scale. Going from 273 to 373 Kelvin, which are the corresponding temperatures on the Kelvin scale, is also a change of 100 Kelvin. Note also that we don't use the word degree with Kelvin. So to convert temperatures, we're going to use this equation, and this is found on your reference tables. If we wanted to use more sig figs, we could use 273.15. But you want to be able to solve problems like these in order to convert temperature. So take a look at these two problems and see if you can figure out how they were solved. And if you have any questions, come come by to see me, but they're pretty straightforward algebra examples. And that's a little bit of an introduction to energy and temperature.